Hello. In previous lessons we discussed about electrical circuit partitioning. We explored how to deal with core couplings, snubbers, and how electrical circuit components impacts your model. In this lesson we will focus more on the signal processing part of the circuit. As explained in the previous module problems and solutions of real-time modeling, sometimes it is needed to execute the signal processing part of the circuit at an execution rate that is lower than is typically used in most applications. If the CPU cannot manage to run code in a given time slot, HIL SCADA will warn us with the computing interval overrun or CIO flag. The fourth generation HIL 404 and HIL 606 can grant you even faster execution rates than the previous generation devices. They also support signal processing partitioning between cores, which allows parallel computation of signal processing code. Signal processing partitioning also makes it possible to exchange data between multiple cores. In order to manage signal processing partitioning, there are two components: CPU marker and CPU transition. CPU marker is used to map a portion of the signal processing model to the specified CPU core. They are only available on devices with multiple user CPU cores. If we double-click on the mask, you can see a marker's identification label that specifies in which CPU core the marked part of the circuit will be executed. CPU transition manages data transfer between components that operate on different CPU cores of the same device. In order for two signal processing circuits that run on different user CPUs of the same device to exchange data, they should be connected using the CPU transition component. Including CPU transition components can introduce a delay of 1 execution rate. You can find more details about this component in the Materials tab. When it comes to signal processing partitioning between cores, there are two modes of operation. By clicking on Model Settings, then Signal Processing Settings, and the CPU Mapping option, you can see the default and execution rate-based operation modes. By enabling the default mode of operation, CPU marker components apply to the connected signal processing component group. Component groups with no CPU markers are mapped to CPU core 0. CPU transition components are used as separators for CPU partitioning. The other option is the execution rate-based mode of operation, which allows model mapping on multiple CPU cores without the need to use CPU transition and CPU marker components. CPU partitioning is done based on the execution rates present in the model. In this way, rate transition components, which are explained in more detail in the documentation link in the Materials tab, can also serve as separators for CPU partitioning. When CPU markers are used, they apply to all components that have the same execution rate. When CPU markers are not used, the compiler automatically maps execution rates to the available CPU cores. Now let's see an example of when signal processing partitioning components should be used and how. For this example's purpose, a HIL 404 is used. As you can see, this example is very simple and contains only a signal processing part. Let's imagine we are performing harmonic analysis for different harmonics. The first harmonic analyzer is used for the first, third, fifth, and seventh harmonic, and the second one is used for the 9th, 11th, 13th, and 15th. The signal processing execution rate is 6 microseconds. Now let's compile this model and run the simulation. As you can see, the compilation finishes successfully, but when we run our simulation, the CIO flag pops up, warning us that the signal processing code can't be executed in the given time slot of 6 microseconds. If we click on the CIO flag, we can see that the user CPU is 100% used. The troubleshooting process implies signal processing partitioning can be a solution. Now let's go back to the model and divide this circuit into cores. Let's put one harmonic analyzer in one core and the other one in another core. Let's choose CPU transition and put the execution rate to TS. Lastly, let's mark which part will be executed on which core. If we compile and run the model again, as is expected, we don't have the CIO flag raised. If we click on that window, we can see that user CPU utilization is equally divided between the cores. Here it is important to notice that CPU mapping in the signal processing settings is set to default. Now let's see how we can use execution rate-based CPU mapping. Let's first use a transition rate instead of CPU transition. The execution rate of the circuit after that component will be 2 times larger than the execution rate before the rate transition. If we compile the model with default CPU mapping, we can see in the message console that this model is in one CPU core as is expected. Now when we run the simulation, we get a CIO error. Let's change the CPU mapping option to execution rate based and rerun the model. In the message console, we can see that the model is divided in 2 CPU cores. If we run the simulation, now we can see that the computing interval overrun issue is solved. Signal processing core partitioning is particularly useful for microgrid systems which contain signal processing-based generic components. Those components will be explained in more detail in HIL for Microgrids course. With this lesson, we've now covered all the important aspects of core partitioning. In the next lesson, device partitioning will be highlighted in more detail. So, see you there. Thank you for watching.